Hi, everybody. I'm going to give you a quick introduction to our class, and then I'm going to give you an introduction to the first module, okay? The way the class is set up is that you have two sets of questions. You have on your own questions, which you should answer while you're reading the text. And then the other set of questions are the study guide questions. And those questions really kind of tell you what the test is going to be like, okay? So in class, we will do on your own questions 1 week. We'll review those. And in the second week, we'll review the study guide questions, okay? And what I will do at the end of the week, we do study guides. So let's say the first time we do Module 1 study guide, at the very end of that class, I'll do a quick introduction to the next module, okay? So it's always going to be on your own 1 week, study guide for that same module, and then a quick peek into the next module, because your homework, obviously, at that point would be take the test for the last module and to start reading the next module. So try to keep up with it, okay? It's always going to be 2 weeks, basically, right? So 1 week on your own, 1 week study guide, okay? And the tests are posted up on the class page, and they're actually going to be paper, so you can download them, and you can, you can answer them right on the sheet and then scan it back in and upload that. Or if you just want to pull it up on the screen, and then just maybe either handwrite your answers or maybe type it out in a Word document and just send that back. It's going to be a lot easier for me to grade this way. It really will be. So anyway, everything you need on the class page. There's videos. There's all kinds of things that go along with the modules. Okay? It's going to be a fun year. We're going to talk about all different types of stuff. First semester, we're going to really be talking about how science works, how scientists set up experiments and how they look at their results and that kind of stuff. Second semester, when we get to that, which is not now, but when we get to that, the second half of the book is actually human anatomy. So you'll learn about the body, okay? And also in this first semester, we're going to start introducing you to the whole idea of evolution versus creation, but we're going to be calling it uniformitarianism and catastrophism. Looking at archaeology and geology and some cool stuff like that, fossils. All right, so that's kind of what we're going to be doing this year, okay? All right, this first chapter is a little bit different than everything else, so I don't want you to be discouraged, all right? It's a history of science. We're going to be learning about the important scientists, okay? We're going to start all the way back in ancient times and up to, current times. Now, what I suggest you do, and I have one on the PowerPoint and posted on the page, I suggest that you make a timeline. Okay, what you could do is make a blank timeline and maybe put each of the scientists on a little index, maybe cut up some index cards and just kind of paste them and just kind of keep practicing. What you're going to need to know for the test, not necessarily when they were, but what they're known for. Okay, what was their contribution to science? Okay, so there's a lot of them we're going to go through. Not all of them are going to be on the test. Remember, we're going to watch the study guide. The study guide kind of gives us an idea for every module, kind of where we're going to go with the test. Okay, so what you see on the study guide is what you really need to know. Okay, all right, so let's jump into this. Okay, you ready? A brief history of science. All right, vocabulary. I always underline vocabulary words, okay? So in the PowerPoints, you always know what's a vocabulary word. So here's 3 that you're going to have for this particular module. The first one is science. Well, what is science? Well, science is an endeavor or kind of a journey that's dedicated to accumulating and classifying observable facts, things that we see, things that we can actually either get a number for, or we can explain it, or not explain it, but we can write about it, okay? And why do we do that? There's 2 parts of this definition. In order to formulate general laws about the natural world. So science is gathering up evidence, gathering up data, right? Classifying that data, putting it into its proper place, order, right? Maybe in groups, and taking that and using it to make laws, general laws about how the world works. That's what science is, okay? Well, the word science, it comes from the Latin word scientia, which means to have knowledge. So really, everything you study is science, right? Because everything you study because you want to have knowledge of it, right? So really that's what the word science does mean. Okay, so scientists do what? They gather facts, they classify them, put them in groups, right? And they use that to make laws about the natural world. All right, papyrus. Papyrus is actually a plant, but it's how the ancient scientists wrote things down. Not just scientists, but any document they had, they would take this papyrus plant and they would put it into paper. They would make it into paper. So you hear the word papyrus meaning the plant, or it could mean the actual paper. So a lot of what we find in the ancient world is things written on papyrus. Okay? All right, and then the last definition is spontaneous generation. Now, this is an idea that came about through Aristotle. All right, we'll talk about Aristotle. He thought that living organisms could spontaneously, like poof, form from non-living things. Now, that may seem silly today, but that was an accepted scientific belief until the 1800s. Pretty recent, actually. When you think about how long ago Aristotle was, right? People believe that. And Aristotle got that idea because he saw some flies growing on meat, and he thought the flies came from the meat. Meat is dead muscle, right, from animal. And so he thought that's where it came from. So that was believed for a very, very long time. Yeah. So we'll talk a little bit about Aristotle too. All right, so those are your 3 vocabulary words. Now for vocabulary on your test, you don't have to have it exactly word for word, but you need to have the basics of what this says. Okay, so in other words, for science, you have 2 parts to it. Accumulating and classifying or organizing data, right? And then using it to formulate law. So that has 2 parts to it. So as long as you have both parts, you're good. But if you want to reword it just a little bit, that's fine. Okay? I try not to pull definitions that are totally different than the way he's got it classified here. Okay? Yeah, you can look in any dictionary and probably get a different description of these. But for some words, you know, try to stick closely to what he has in the book. All right, so we're going to go all the way back before 600 BC, way, way back. And the first scientist we're going to look at is a man named Imhotep. He was an Egyptian physician about 2650 BC, long time ago. Now, back then, many people didn't call these people scientists because they did everything by trial and error. They really didn't try to figure out why things worked. Medicine was, well, let me try this. Did that work? Oh, great. Okay, write that down. Well, that didn't work. Write down not to do that again. That's all they did. They didn't really say, well, why did it work or why didn't it work? Now, sometimes they were right. For instance, they would put moldy bread on wounds, and it would actually help. Well, why is that? Well, one of the molds that we see on bread is penicillium, which is where we get the antibiotic penicillin, right? If bacteria gets into a wound, you know, you can have an infection. That's from bacteria growing. So we give you an antibiotic, which is against bacteria. Penicillin is one of them. In fact, that was the very first antibiotic that we ever came out with. But it was because of moldy bread, what it was from. Now, did they try to figure out that's what the reason was? No. They just knew that putting moldy bread helped heal wounds. They would give people poppy seeds for pain. Well, poppy seeds is actually where we get today's painkillers, codeine, morphine. They actually are derived or pulled out of the poppy seed plant. So they didn't know why. They just knew that giving someone poppy seeds helped them with their pain. So those are just kind of 2 examples of them just trying stuff and seeing if it worked. If it worked, that's great, right? But a lot of times they had things that didn't work. So they wrote all this down on that papyrus paper I told you about, right? So they would write down moldy bread for wounds, you know, poppy seeds for pain, you know, so they knew that would kind of work. All right. Also during this time period, the Mesopotamians actually started using a pottery wheel. That was kind of cool that they could actually make pottery. Up to this point, they didn't have anything like that. And the Chinese, they were doing a lot as well. They were working on compasses. And that's, of course, helpful, right, to be able to get around. All right, so this is kind of the beginning, sometimes the first inkling, the first attempt to be scientists. Were all these scientists really? Would we define them by our definition? Were they gathering facts? Yeah, they were. But were they trying to explain anything? Were they trying to explain the world, making laws? No, they weren't. And that's why we generally don't call someone like Imhotep a true scientist. Okay? So here we've got some things that man is starting to kind of figure out here, right? All right, so that's before 600 BC. Now, 600 BC up to about 500 AD, okay? So that's about 1,000 years. The ancient Greeks started collecting data, and they tried to explain things. In fact, the Greeks usually, that's what they did, right? They sat around and they thought about things a lot. Thales, he was one that studied the heavens and the movement of the planets. He was the first one to ever predict a solar eclipse. That's pretty cool. So Thales was an astronomer. Anaximander was one of Thales' students. And this is kind of sad, but he tried to explain the origins of life, the beginning of life, but without a creator. He believed all life began in the sea. That's kind of evolution, isn't it? That's what evolutionists say, that there was no creator, that things just kind of came out. Things spontaneously came about, right? So when people say that Darwin was the first one to talk about evolution, that's not true. You can go all the way back to this man, Anaximander, and probably before him even. They were thinking about how did life begin, but we don't believe there's a creator. Very sad. All right, Anaximenes, he was a co-worker of Anaximander, and he believed air was the most basic substance in nature. He said everything around us is made of air. Now that's not true, right? You probably know that, right? It's not made of air, but this is what they believed at this point. All right, so we've got these ancient Greeks that are starting to not just gather information, but they're starting to kind of answer questions. Whether they got it right or not, I mean, they may not have got it right, but they're starting to think about that data they collected, all that evidence they collected. They're trying to make some reasonable conclusion or explanation as to what they mean. Okay? Also, Leucippus, he was about 150 years after Anaximenes. He said that matter, everything around us, is composed of little units called atoms. So he's known as the father of atomic theory. Isn't that amazing? So if we go back here for a minute, we had Anaximenes saying everything was made of air. About 150 years later, Leucippus comes along and says, not air, but there's these little tiny things called atoms, right? Now, Democritus, he was a student of Leucippus. And he took that idea and went a little bit further with it. He noticed that, if you looked out on the beach, for instance, you would see sand. And it looks like one thing. But as you get closer, you realize sand is made of smaller particles. So that was kind of where they got this idea of everything is made of something smaller. There's two really cool experiments that you can do, experiment 1.1 and 1.2, and there should be videos of these also. A word about experiments. Try to do the experiments whenever you can. Okay, most of them are things that you can do very easily at home, very easily, probably stuff you already have around the house. You don't need to buy a big kit or anything, but try to do the ones you can. But if you can't do it for some reason, make sure that you read through the experiment, right? Read what you need for it and how you do it, and then he always gives an explanation of it afterwards in the text. Okay. So make sure you do understand the experiments, even if you haven't done them. Okay, and we'll try to talk about them in class as well. And if you have questions, of course, you can ask when we go through them. Okay, but these experiments actually look at the work of Democritus about how atoms actually work. Now, did he know they were called atoms? Leucippus kind of called them atoms. But did he understand what they were, like we do today? No. But he did have the first idea that, hey, everything is made of something smaller. Some other notable Greek scientists around the same time, we already mentioned Aristotle. We call Aristotle the father of life sciences because he was the first one to actually classify animals and plants. He put them into groups. We use what we call the Linnaeus system. That's another scientist we'll look at. But Aristotle started classifying things too. A little bit different than Linnaeus did later on. But he did start to say these animals have things in common. So he kind of put them in groups, right? He did a lot of study with that. Aristotle was very well respected. I mean, like I said, even up to the 1800s, people were still following Aristotle. Remember our vocabulary word, spontaneous generation? Remember that life came from nothing? Life just kind of appeared spontaneously. That was believed until the 1800s because they said, hey, Aristotle said it. Must be true. Aristotle's a really smart scientist. If Aristotle said it's true, it has to be. You know, and we'll see later on, people are going to start questioning some of the things that Aristotle said. But it really was much, much later. I mean, people just believed it. And that's why science, in my opinion, really kind of stopped. You know, science should be a journey, right? And it kind of stopped because people said, oh, well, Aristotle said this is true, so it's true. So it led science in the wrong direction for a long, long time. I just wonder what kind of advances would we have today if we hadn't wasted that time between Aristotle and the 1800s, believing something so wrong as spontaneous generation. Yeah. Now, this is a quote I put in here from Dr. Weil on page 9. He says, thus, no scientist's work should be supported because the scientist was great. It should only be supported because the scientific evidence supports it. Everybody thought Aristotle had the final word. He's a great scientist. Whatever he says must be true. That's not how science works. No matter how smart a scientist is, his work should always be repeated. You should continue to gather evidence. And if it goes against what that scientist says, then you have to work with that, right? You have to say, hey, he's not right. We need to go another direction maybe, right? Now, why did it last till the 1800s? Because, well, they did a lot of experiments that were not really set up right. They were kind of set up in a way to kind of prove Aristotle, to show that Aristotle was right. They weren't really doing very good experiments to test his idea of spontaneous generation. And again, it wasn't until the 1800s, and we'll see the scientists in a little bit here, who came along and said, well, what if we do this experiment? Oh, see, that shows it's not true, right? So it's really important. What you want to get out of this whole story about Aristotle is that we don't trust the scientist because he's great. We trust the evidence, okay? That's what we have to go by. I mean, Einstein, brilliant man, right? Is he right? Well, maybe he's not. We have to keep testing his stuff too. Just because he was smart and knew a lot of things and contributed a lot doesn't mean he was right on everything, right? So Aristotle was wrong on spontaneous generation. He was correct on a lot of other stuff, though. I don't want to bash him completely here. He was a good scientist. He did a lot of good stuff. But in this particular case, he was wrong. So always look to the evidence, not to the scientist. Okay? Archimedes, you may have heard of him before. He's the one that ran down the street with no clothes on, yelling, Eureka, Eureka, which means I found it. He was known for showing how math and science could come together and work with fluids. He was trying to find whether or not king's crown was really made of gold. And so he did a lot of stuff with what's called density, how much matter is packed into something. And so by putting it in the bathtub, actually by him sitting in the bathtub, he realized he was displacing or removing the same amount of water as his weight, right? And so he said, I can use that to figure out whether that's really gold or not. So he was really excited. He was just taking a bath. And he got really excited because it just dawned on him, this is how I can figure it out. And so he jumped out of the tub and ran down the street with no clothes, yelling, Eureka. All right. Ptolemy, the P is silent. Ptolemy, he was one of the first that tried to figure out the solar system, the planets and the stars. And the Ptolemaic system, which is named after him, or what we call the geocentric, Earth-centered, so that the Earth was in the center and the sun and the planets and the stars all revolved around the Earth. Now that was believed for a long time too. So that's the geometric or geocentric or Ptolemaic system where the Earth is in the center. Okay? That's Ptolemy. All right, now, scientists are starting to gather data and question things, right? They're doing really good. Well, we got to between 500 and 1000 AD, we kind of stopped. The Roman Empire was very, very, very much in charge of the world. They said, it's all no need for science. They said, does it work? That's great. Doesn't work? Okay, thanks for letting us know. But we really don't care why it works. We have no desire for that. You know, if you can make my life better, awesome. You know, that was just their idea. Science was not encouraged. You know, they didn't care to explain things. They had no desire to do that. So what that kind of led into is something called alchemy. You've heard of the alchemists. Really, really bad science. They thought that they could take lead or other things and turn it into gold. Wouldn't that be great if we could just take something and turn it into gold? Because gold's valuable, right? It's like making money. That's what they thought. But here's the problem. They were just mixing all kinds of stuff together. It wasn't just bad science. It was very dangerous and even deadly in some situations. They would say, well, what happens if I mix this and this together? Well, when you take chemistry, you'll see that's not such a great idea. I mean, they had lots of explosions and fires and things just trying to make gold. What they were really seeing is chemical reactions. They weren't making gold, right? So this is what happens when we don't care about science. We start doing crazy stuff like alchemy. Now, in defense of alchemy, though, many of the scientists who were alchemists at the time ended up, you know, learning from those things and actually working with chemistry later on. You know, the science of chemistry kind of came out of alchemy. But it wasn't good science. That's the thing to remember. Not very good science at all. And it's because, you know, there was just this idea of science is not important. Don't worry about it. So alchemists, I wouldn't call them true scientists, right? Because they were just kind of doing whatever, and it wasn't very safe. So this led us into what we call the Dark Ages. Now, if you've studied this time period in your history books, you know this was a time when people weren't really communicating very well. You know, science really requires scientists to kind of communicate with one another. You know, of course, in this time period, communication was very slow. You know, somebody in one country didn't know what somebody in another country was doing. It took a long time for that information. Today, what happens with scientists? Well, they post it on the internet, right? So one scientist says, oh, they're doing something similar to me. Let's talk to each other, right? But that didn't happen in the Dark Ages. So this is an important thing for you to remember, this bold. Scientific progress depends not only on the scientists, but it depends on the government and the culture. Remember, the Roman government said science was not important. So guess what the people thought? Science is not important, right? So it wasn't just the government said it wasn't important. You've got people saying it's not important. So why bother doing science, right? So when we think about science moving along, we have to have support of the people, the culture, and we have to have support of those people that are in charge, right? I mean, think about today. What if government stopped funding research? Well, we may not learn about maybe some disease or work on a cure, right? The government doesn't care. And if people don't care, we're not going to find a cure, right? So it's still true today that we have to have government support and we have to have the support of the people. If not, science just doesn't go anywhere. Now, you think, okay, nothing happened then during this time. Well, that's not necessarily true, because there's always people that are going to do stuff, right? God always has his people, right, lined up, even in the midst of the Dark Ages, to continue things. So there was still stuff going on. There were people that were making observations, making discoveries. They just weren't as much of it as there should have been. Okay, for instance, the Chinese. Remember, they were working on compasses and stuff. But they were also looking at the constellations. They were studying nebulas and supernovas, right? Those are exploded stars. They were making note of that stuff. They were writing it down. They were keeping track of it. And then the Roman Catholic monks, they're the ones that usually were isolated. They kept to themselves. And they would write down stuff. They would write down things that were happening around them. They kept really, really good records. So even during a time when there was not a lot of communication and the government didn't care about science, which meant the people didn't care about science, there were some people that were caring and they were writing stuff down. Okay? So that's the Dark Ages. Science progresses by building on the work of previous scientists. Now that's important because if they're communicating, they know to say, oh, this scientist has already done this. This even today. This scientist did this. I need to do that plus a little more, right? That's how we keep doing this, right? That's how science moves along. So that communication is really important. The support of the government, the support of the people help science move along, okay? So here we are in the Dark Ages. Now, even during this time, if you read about the Dark Ages, the church actually set up hospitals. What they knew, they weren't hospitals like you think of today, but they did attempt to try to help people, right? The church really is the one who began hospitals. And so even during this Dark Ages, they took the information that they knew, the treatments that they knew, and tried their very best to treat people and help them medically. Oftentimes it wasn't very good, but it was better than nothing. It really was. So we can thank the Christian church for, at least even during this Dark Ages, attempting to help people, right? All right, now get to 1,000 to 1,500. For that time, remember the Romans are in charge, right? Now they believed in many gods, right, little g. And remember, no reason to explain things. We really don't care why it works. Doesn't matter, right? Well, the church, though, believes what? One God, right? And they believe it's a God who created our universe, right? And that he's created laws that never change. So we can know about the natural world. We can figure out stuff. So here we've got the Romans, right, saying, doesn't matter, many gods, we don't know what they want. So they're looking at one God who created laws that we can understand, right? So what we start to see now is the Christian church is kind of taking over from this Roman view. So there was a change in attitude from the Roman way of thinking to the Christian way of thinking. Okay? And so we've got some scientists that came out of that period, that transfer from Roman understanding, right? Roman thinking to Christian thinking. Robert Grosseteste, he was a bishop in the Roman Catholic Church. And we call him the father of the scientific method. He said, we need to really be organized in the way we do science. We need to not just do like the alchemists did, to say, hey, let's just throw some stuff together. We need to be orderly about it. Because he said God is orderly. He does things in order. We need to be that way. And so he came up with the scientific method, which is, remember, if you've learned this, is, you have a hypothesis, you test it, right? You get data from it, you make a conclusion, right? So you have a hypothesis, a guess, you test it, gather data, make a conclusion. You just kind of keep going on and on like that. He said that's the way we should do science. So that's Robert Grosseteste. Dietrich von Freiberg, he was a priest in the Roman Catholic Church, and he used that scientific method to actually figure out, why do we have rainbows? That's a great thing to learn about, right? Why do we have rainbows? And so we call him as the priest who solved the mystery of the rainbow. We know what rainbows are today, right? But back then they didn't know. And so he did made a hypothesis, and he did some testing, and he came up with a conclusion, and he kept testing it over and over again. And so I think I figured out why the rainbow's there. So von Freiberg is a priest that figured out the rainbow. Roger Bacon, he was a Roman Catholic theologian. That's someone who studies the Bible, right? Tries to explain it. He was a huge follower of that scientific method. His statement here is kind of mine. That we can learn more about God by studying science. I believe we can understand the Creator if we study what he created, right? That's what Roger Bacon said too. He says we need to use that scientific method to really understand who God is by studying science, by studying the things that he's done, right? So that's Roger Bacon. So I like him. That would be my statement if I was Roger Bacon. Thomas Bradwardine, He was another bishop in the Roman Catholic Church. He started to question the teachings of the church a little bit. The church teachings were changing at this time too, and he was actually an influence on the Reformation. If you know about the Reformation, where really questioned the Catholic Church, where we get the Protestant denomination. So he was a big part of that. But here's the big thing Bradwardine did. He challenged Aristotle. Remember I said Aristotle was accepted. He was a great scientist. People believed everything Aristotle said, including the church, accepted what Aristotle said. But he started doing some things to say, hey, I don't think Aristotle was right in this area. Now, he didn't get very far with a lot of it because people, again, still believed Aristotle. But he was one of the first ones to actually question Aristotle. Said, I don't know if he was right or not. Be kind of like us today going, I think Einstein's completely wrong. People would be like, really? Now, maybe Einstein is wrong. I don't know. Well, who knows what's going to happen in the future. But I'm just saying that's the influence that Aristotle had. And so for Bradwardine to question that was pretty bold. So he questioned and challenged Aristotle. Nicholas of Cusa, another priest, studied the planets and the stars. And he was the first one to say, I don't think the Earth is in the center like Ptolemy said. I don't think this geocentric view was right. The church thought it was right, though. The church says the Earth is in the center. They believe Ptolemy, right? But Nicholas of Cusa said, well, maybe that's not true. Maybe the Earth is not the center. Did the Roman Catholic Church like that? No, they did not. Earth is the center. But we're going to get into some scientists who question that even more, because we're going to get now into the Renaissance, which is the 1500s to middle 1600s. And a man named Nicholas Copernicus came about. And he published a book. He published it, I'm not sure if it was right before he passed away or whether it was actually published right afterwards, but it was towards the end of his life that he actually came up with this actual theory. He came up with what we call the heliocentric theory, which is a sun-centered theory, where the sun is in the center and the planets revolve around that. Well, the church didn't like that. Remember, they liked the Earth being in the center. So Copernicus was publicly denounced, like, that you're wrong. What you're saying here, it goes against the church teaching. And then interesting, the church teaching was considered what science was. They controlled the science. So they said, no, Copernicus, you're not right. The sun is not the center. The Earth is the center. Now, he didn't live long enough to argue his point, but he wrote that book that said the sun was in the center. Now, he was denounced, but at the very same time, another man named Andreas Vesalius wrote a book on the human body. And it changed the way we understood medicine. And the church accepted that. The reason this was important is before Vesalius, the only thing we knew about were animals. It was frowned upon to look at a human body, a dead human, to look inside of a human body to see how humans work. Now, we're similar to animals in lots of ways, right? But there's some things that are different. And so we can't completely go on what an animal's body looks like to figure out how a human body works, right? Well, Vesalius was one of the first people to actually look inside of a human body. He looked at cadavers. That's a dead human body. He actually looked inside cadavers to say, oh, this is a little bit different than animals. We have a lot in common, but there's some things that are different, and he's the one that figured this out. And the church was okay with that at this point. So here's these two scientists. You've got Copernicus saying the sun is in the center, not the Earth. The church doesn't like that. But Vesalius now starts to look inside the human body and explaining the differences, and the church was okay with that one. Kind of interesting. A couple more scientists around the same time. You have Johannes Kepler. He also studied the planets, and he's known for Kepler's law and the idea that planets do not go in circles. If you look at a picture of the solar system, sometimes we draw them in circles, don't we? But really, they're more of an oval or an ellipse. And Kepler mathematically figured that out. And there is a real fun little activity you can do, an experiment you can do to actually see what we mean by an ellipse. It is not a circle. So he was studying the planets, and he said things go in these ellipses. All right, Galileo Galilei. Now, we usually go by his first name, don't we? We're on a first name basis with Galileo. His last name is really Galilei, but we call him Galileo, right? He did a lot of experiments that kind of show. Remember Bradwardine said Aristotle probably wasn't right. He agreed with a lot of the stuff that Bradwardine was doing. He repeated some of his experiments and showed again that Aristotle was wrong on some stuff. Didn't mean people changed their mind, but they had some evidence. Did a lot of work with telescopes. But here's the big thing he got in trouble for. Remember Copernicus said the sun is in the center, not the earth, and the church didn't like that? Well, here's Galileo coming along, gathering even more evidence to say, you know what, Copernicus is right. But once again, the church rejected it. He was actually forced to recant, that means take back his what he says, and denounce the heliocentric. He had to publicly say, Copernicus is wrong. The earth is the center. Now, why did he have to do that? Because the church had a lot of power at that time. And the church really controlled the culture. Now, think about this. If you really believed that the sun was in the center, would you stand up and say that you didn't believe that? Well, here's what would have happened to Galileo. He would have been excommunicated from the church. It means he would have been rejected by the church. And you think, well, okay, just go find another church. Well, it wasn't like it is today. You know, if you have a disagreement with your church for whatever reason, yeah, you could go to another church. But the church then was the culture. So he would have been shunned, completely shunned by everybody, because to not be a part of the church was just unheard of. So he thought it was better to say what they wanted him to say, but in private, he continued to work on the heliocentric view. So we'll talk more about that in class. You know, it's one of the questions in your book. Should he have done that? Well, we don't live in Galileo's time, so it's hard to say how we would react if we were him. It's different than maybe today, but the church then had so much power. They were the culture. They controlled the culture, and so he would have been rejected. But he supported Copernicus. He said, no, the earth is not in the center, the sun is. Okay? Another scientist around the same time was Blaise Pascal, known for studying the effects of atmospheric pressure and something called Pascal's law. So he studied air and liquids. All right, now we're getting into the era of Newton. Y'all know who Isaac Newton is, right? This is 1660s to mid-1700s. Sir Isaac Newton, considered to be the greatest scientist of all time. He's right up there with Einstein and some other people. He did a lot of work. He did the laws of motion. He did the universal law of gravitation. You'll learn more about those when you take physical science. He developed calculus. You know why he developed calculus? It's a higher math. He said, the math that we have does not explain the science that I'm trying to show you. So he had to come up with his own math to explain his science. He did stuff with light. He redesigned the telescope. Remember, Galileo and others had worked on the telescope. He kind of redesigned it. But here's what he's really known for. He was a very devout Christian. There's a little write-up on him in there. He doesn't necessarily have the same views about God that we would have today. You may even think he's kind of way off base. But he did believe in God, and he trusted God. But he did a lot of stuff in his mind to show, kind of like Roger Bacon, that said, we can learn more about God if we study science, right? And so that's really what you can think about for Newton. That he even wrote devotionals and things like that, and it all pointed back to the science, really, to show who God was. Again, it's one of my favorite people. If I had a chance to sit down for lunch with someone, I would probably want to meet with Isaac Newton. I would love to talk to him. I can tell him what he was wrong about and the things we've learned from him. But, he kind of started it. He started a lot of cool science that, yeah, he was a little bit off on a few things, but like his law of motion, universal law of gravitation, we still use those. We still use calculus, right? but I could update him a little bit maybe on some of the stuff we've learned since his time period. But one of the greatest scientists of all time. Robert Boyle, you'll learn more about him in chemistry, but he learned things like how gases work. He's kind of the modern chemistry. Remember we had the alchemists, right? I believe Boyle came out of the alchemist movement. And he really did what we today would call chemistry. But he did a lot with gases. There's Boyle's law about how gases work. And then von Leeuwenhoek built the first microscope. Now, this is big news. Up to this point, people had no idea that there were things smaller than what they could see with their eyes. They had no idea that there was another whole world of microscopic organisms. No idea. When Leeuwenhoek came up with the microscope, it started a whole new area of science. Big deal. It's where we saw, parasites and microscopic algae and all kinds of things that we had no idea were there. So Leeuwenhoek, pretty cool guy, built the first microscope. Now we get into what we call the Enlightenment. So if you've studied history again, you may have read about this. And also the Industrial Revolution. This is where we started to make stuff to help us live a better life. Now, this has two things. One is good and one is bad that's happening during this time. It was during this time that people started to look past the scientists. Remember I said we don't look to the scientist because he's great. We look to the evidence, right? Up to this point, people weren't necessarily doing that. During this time period, we really started to say, hey, what was that Aristotle said? Let's go test that again. I know Aristotle is great, but maybe he's wrong. Let's test his work and let's see whether or not what he said is true. And they started doing that for all scientists. They started really testing to see whether or not what these scientists had said was correct, right? So that's a good thing. But here's a bad thing that happened also during this time. A lot of scientists started to say, well, we don't need to mix our science and our scriptures. If you believe in the scriptures, that's fine. But that has no place in science, right? If you notice, all these scientists we just mentioned, they were priests, they were bishops, right? They were Christians, right? Isaac Newton, Christians, right? And they thought that studying science was a way of glorifying God, right? Explaining, how God created everything. But now we start to see scientists that are saying that's not necessary. We don't need to bring God into this. We don't need to have the scriptures confirm what our science is saying. Because here's the thing. If the scripture is telling you one thing and your science is telling you something else, which one are you going to believe? Well, up to this point, if it didn't line up with scripture, they would say, well, my science must be bad. I did something wrong with my experiment, or I'm coming to a bad conclusion, right? But now scientists are saying, we don't need to compare it to scripture. We don't need to see whether or not that lines up with what God has said. We don't need that. So that's a bad thing. So we're starting to examine things more critically, but at the same time, we're rejecting the authority of scripture. And we're not applying it to our science. So that's a bad thing. So this is up to the early 1800s. So this is when we started to, the top one, the good thing. This is when we started saying, hey, Aristotle, not so right. But it's also where we started to say, we don't need God. All right? Carolus Linnaeus, I mentioned him already. Remember Aristotle had done some organization of living things? Well, Carolus Linnaeus also did the same thing, and he wrote a classification system, and it's the one we generally use today. Kingdom, phylum, class, order, family, genus, species. You've heard of that, right? That's the Linnaeus system. Okay? He was a huge believer that God did things in order. He was very organized. And that if we're going to study living things, we need to organize them as well. It will help us understand them. But why do we do that? Why do we organize them? Well, if we can find a group of animals that have things in common, right, then we can study that, comparing that to something else, right? These all have something similar. So it makes it easier for scientists to study things when you're studying things that are similar, right? Right. Another scientist during this time was Lavoisier. He was a chemist and came up with the law of mass conservation, which says that matter is neither created or destroyed, but can only change forms. He actually named a lot of elements on the periodic table. You know what the periodic table is? Lists all the elements. he named a lot of them. But the law of mass conservation basically says this. All of the matter, we define matter for you. Matter is anything that takes up space and has mass or weight. That's everything around us basically except energy and light, right? So everything around us is matter, which means it's made of atoms, okay? So what he said is that matter, we don't create it, we can't destroy it. It can just change forms. What that means when we compare it to scripture, when God was finished on day 6, when he finished day 6 and he rested on day 7, that rest meant he was finished, right? So he was all finished. So everything that we have is here, right? So law of mass conservation says, okay, well, you can take hydrogen and oxygen and then you can put them together to make water, but I still have hydrogen and oxygen, don't I? Right? So he says things may change form. Things may come together, atoms can join together, make molecules and come apart, all that. But he says, everything's here. Everything we need is here. All the atoms, everything is right here. So the law of mass conservation is really important when you take chemistry. Okay? John Dalton, remember Democritus? We call him the founder of atomic theory. Remember, he's the one who said everything is made of something smaller. Remember, in his teacher Leucippus. So Democritus and Leucippus kind of got us thinking about atoms. Well, here's John Dalton coming up with a much more detailed idea of what the atom is like. And we actually still use a lot of what Dalton said. He was pretty accurate in what he wrote. So John Dalton, we consider him the founder of modern atomic theory. And we've built on it since then. The things we know about the atoms today, Dalton didn't even know. But he kind of got us started on a really good path to understanding what the atom looks like. Okay? And we said this was also the time of the Industrial Revolution. This is where we started to make inventions that made life easier for us. Things made work faster, made it easier, made it more productive. We could get more things out of it. So a really great time when we started, using our brains now, right, to make things that are actually helpful to us. All right, the rest of the 19th century, up to the 1900s. Charles Darwin. He was the one who proposed the theory we now call evolution. Now, remember way back, we had an ancient scientist who also said we don't need a creator, right? Remember I said it started way back then. Darwin is the first one that kind of put it all together and published it in a book. The book was called On the Origin of Species by Means of Natural Selection or the Preservation of Favored Races in the Struggle for Life. There's a lot we can unpack in that title. We'll talk more about it in class, but he came up with this book that said, we don't necessarily need a creator, right? We can explain things just through science. Yeah. Remember the Enlightenment? We just said the Enlightenment was when people started to say we don't need to confirm scripture. We need to look just at science, right? Well, this book kind of put a stamp on that and said, okay, we don't need to look at God when we do science. This began back in the Enlightenment, right? We don't need God. Darwin kind of confirmed that we don't need God. Believe it or not, he was studying, the Bible. He was a Christian. What happened to him, we don't know. Some people say, oh, he recanted all this and said, that evolution was wrong and that just recanted on his deathbed. But there's no evidence of that. I mean, we believe he took that theory of evolution to his grave. But here we are trying to explain life without a creator. Now, I'm going to give Darwin some credit here because some people like to just completely bash him because if they're against evolution, they say Darwin was wrong. Darwin was a good scientist. He gathered lots and lots of data. I don't necessarily believe in his conclusion of that data, but he gathered a lot of information. He was very, very detailed. He spent a lot of time on the HMS Beagle and went to the Galapagos Islands and studied lots and lots and lots and lots of animals and journaled, wrote it all down. So he was very, very good at that. So it's one of those things where you've got great data, but we come to different conclusions, right? His conclusion was that evolution was true. Other people would look at his data and say, oh, that shows creation, right? All right, so When I give him credit as being a good scientist, I just disagree personally with his conclusion. Okay? Here's one thing, though, that Darwin did that was very, very good. Up to this point, people believed that creatures, animals, for instance, stayed the same, but they never changed. It was called the immutability of species. In other words, it would say that, okay, an elephant has always been an elephant. When God created the elephant, he created the elephant in the very beginning, and it's still the elephant. But if you look at Scripture, what does it say? It said he created kinds. So from that elephant kind, well, we got different types of elephants. We have other animals that were elephant-like, right? That are no longer with us. So we know that things came from a kind, and that things do change. And not only do they change, but even if you looked at an elephant maybe 100 years ago versus an elephant today, you might see some changes in it. It's still an elephant, right? It's still an elephant. It's just maybe changed a little bit. And that's because of something called natural selection. Animals can adapt. Organisms can adapt and make changes. People, if we were to look if we had a picture of Adam and Eve in the garden, we would know they were human, but they might have some things that are a little bit different than us. Just slight things to adapt. You know, they might have been taller or shorter, or they might have had different facial features. There could have been all kinds of things that they had that humans today don't necessarily have, because we have changed through natural selection. Here's the difference between that and evolution. Evolution says that one organism becomes another new type of organism, which becomes something else. Make sense? Where natural selection says, no, it's still this organism. It's just changed a little bit. It's still the same organism. Okay? So natural selection, sometimes you hear it a lot with evolution, but really natural selection is okay even with creationists, because we do believe that things can adapt. They can adapt to their environment. I always think about the Tower of Babel. Think about the story of the Tower of Babel, right? Everybody was in one place. And when God confused their languages, what did they do? They had to travel, right? They had to move. And probably during the same time, we had, the continents moving because of the flood, right? The continents are moving. So people started to be with the people they could talk to, right? And they started moving, right? They started moving around the world. They were exposed to different climates, right? So people who were in warmer climates started producing more melanin in their skin. It's already in our DNA to know how to make melanin, right? So they started making more melanin, so they tended to be a little more dark skinned. Those who were in colder climates didn't need as much melanin, so they were more fair skinned. So we start to see the nations, the races, so to speak. We're one race, human race, but what we call races, the ethnicities, I should say, probably. We start seeing that happening, and that's because of natural selection, actually. That's different than evolution, right? So a lot of people reject what Darwin said, right, about evolution. But he really did a lot of good for biology. He helped us understand the immutability of species, that things do change. Natural selection does allow us to change. Adaptation, things adapt to their environment. They don't change from one species to another, from one type of animal or organism to another, right? They're the same thing. They just have adapted. They've changed a little bit. So he did a lot of good for that. We can reject his theory of evolution if we want, but we have to understand that he was still somewhat of a good scientist. Okay? We'll talk more about it in class. Okay? All right, Louis Pasteur. All right, remember Aristotle and his idea of spontaneous generation, that things come from, living things come from dead things? Louis Pasteur, he's the one. This is when we finally said Aristotle is wrong. He did an experiment, and it was a very simple experiment, but it showed spontaneous generation does not happen. So all this time, people were still believing Aristotle, even though there were some people along the way that were kind of questioning it. It wasn't until Louis Pasteur did this that people said, oh, okay, he's not right. long time to believe something that's totally wrong. Pasteurization. We pasteurize a lot of our foods, like milk, for instance. Look on the milk container, it'll say pasteurized. What do we do with that? We heat it up really, really quickly and cool it back down to destroy the bacteria. So it was a way of kind of sterilizing things. And he also did a lot of stuff with vaccinations. All right, Sir Charles Lyell. Charles Lyell was a geologist right around the time of Darwin here. He had a huge influence on Darwin. In fact, part of what Lyell said helped Darwin develop his theory of evolution. This is what Lyell said. He said the earth is millions of years old. Up to this point, that was looked at as being crazy. No one thought the earth was that long. You know, they were looking at scripture, and they were doing the genealogies in scripture, and they said the earth is not millions of years old. Creationists today believe the earth cannot be more than maybe 10,000 years old. It's not millions of years old. But Charles Lyell, he was actually a theologian as well, but somehow he eventually, I believe, rejected God over time. But he believed that the earth was millions and millions of years old. And today we even look at billions of years, right? But so Charles Lyell kind of planted that idea in Darwin, which helped Darwin develop his theory of evolution. Because in order for evolution to be true, we need to have millions of years. If the evolution is true, we need to have a long time period. And so Charles Lyell kind of planted that idea in Darwin. All right, Gregor Mendel, he was a monk, Augustinian monk, and he came up with the idea of genetics. Mendel liked to plant things. He liked to grow stuff, and he had pea plants that he would grow. And he kind of noticed that sometimes he had plants that didn't look anything like the other plants. And so he started thinking, okay, well, if I take the seeds from these plants, what offspring can I get? And so he did all of this stuff with genetics, which is where you get part of your DNA from mom and part of it from dad, right? And that's why you look kind of like mom and a little bit like dad, maybe, right? That's genetics. That's looking at your DNA. What's contributed? Well, he did it with plants. And the rules apply to plants just like they do for people and animals. So he did a lot of stuff with crossing plants, self-pollinating plants and crossing things together to see what kind of offspring he would have. And so he came up with the idea of genetics. And so the whole study of genetics really is really based off of what Mendel did. And it was all using pea plants. Pretty cool. But he was a monk. Remember, monks were kind of to themselves. So he had lots of time to grow his pea plants and to come up with this idea of genetics. Michael Faraday, bold Christian, very, very outspoken Christian, actually, did work with electricity and magnetism. He was called the electric giant. So he did a lot with that. And then James Clerk Maxwell, he kind of worked with Faraday. He came up with electromagnetism. He's the one who figured out that electricity and magnets are really two sides of the same coin. If you take physical science, you'll learn more about Maxwell. Maxwell was actually homeschooled. And he's the founder of modern physics because it's all about electricity and magnetism and things like that. James Joule, he took some of the work of Lavoisier and said, you know what? Remember that law of mass conservation that said matter is neither created or destroyed? He says, same thing with energy. We can't make energy. We can't make it. We can't destroy it. It just kind of changes form, right? It just changes into something else, another type of energy. Like, for instance, you can have stored energy, right? And then you can have kinetic energy, which is movement, right? It's still energy, just changes form. So he did a lot of work with Joule, and he came up with the first law of thermodynamics, right? Which says that energy cannot be created or destroyed. It can only change form. So very similar to the law of mass conservation. So now we generally say energy and matter. And the joule is actually a unit of measurement when we're looking at energy. We talk about how many joules of energy there is, so we name it after him. You discover something and we name things after you. So we named the energy unit joules after him. All right, modern science. This is up to the present. Not to today particularly, but just early 1900s up to now, what we know. These three men right here, Max Planck, Albert Einstein, and Niels Bohr, worked together on atomic theory. Then we had Democritus and Leucippus way back in ancient times. Then we had Dalton, right, came up with the modern theory of the atom. These guys took it to the next level. Max Planck said energy is in packets called quanta. Came up with the idea of quantum mechanics to explain how the atom works. Actually helped explain some experiments that Newton's laws didn't quite explain. Remember I said Newton wasn't completely right about everything. He was right about a lot of stuff though. But he kind of tweaked it a little bit and said, this is probably what Newton meant. And so Max Planck did that. He worked with Albert Einstein. Everyone knows Einstein, right? Again, he used Planck's idea to explain what we call the photoelectric effect, which you don't need to understand all this, but he kind of, again, helped clarify some of the stuff that Newton couldn't. But the thing he's known for is the general theory of relativity and the special theory of relativity. Again, if you take physical science, we spend some time talking about those two theories, but they actually help us understand how the universe works. For instance, Albert Einstein said that we have something called space-time. It's like a blanket, and a heavy object like the sun kind of puts a dent in it. And Einstein would say, this is kind of hard to think about, he would say the planets are not going in ellipses. They're actually going in a straight line. And the reason they look like they're going in a circle is because the sun is so heavy that it's making a well. And that so something that's moving actually ends up going this way so it doesn't fall into the well. Really deep stuff, but you don't need to understand it completely. Just understand that he came up with the theory of relativity and the special theory of relativity. And another person who worked with them was Niels Bohr. You probably have seen pictures of atoms where you see the nucleus, which has protons and neutrons, and then electrons in a circle going around it. Almost looks like a planet, right? Planets going around the sun, like a solar system. Niels Bohr came up with that idea for an atom. Now, it's not how atoms look. Atoms are very three-dimensional, but it was very practical to draw the Bohr model. And so we use the Bohr model a lot in chemistry. But he's the one who came up with the idea of, okay, let's put the neutrons. Now, other people have done experiments to show where things were in the atom, but he said, okay, let's draw it. Let's put the neutrons in the center, let's put the protons in the center, and then let's put our electrons on the outside. And that was kind of his idea. Okay? All right. A lot of scientists, but what I've got here is a timetable. Now, you could cut these out if you want and maybe make a long timetable on your wall or something. Excuse me, but here's the time period, the scientists, and this is what they're known for, and that's what you're going to have to use on your test. You're going to need to know the scientists and what they're known for. So there's several pages of these, okay? All right, so keep it simple. I know it looks like a lot, but it's really not that much. And we're going to go over some questions in class to help you kind of remember these guys, okay? But just kind of go through and say, okay, what did Anaximenes do? Oh, he said air was in everything. Ptolemy, oh, the Earth is in the center, right? Copernicus said, oh no, the sun is in the center. So you can kind of relate some of these to each other. Because what's happening is, if you notice, the later scientists are either confirming what the earlier scientists said, or they're taking their ideas and improving on them or correcting them, right? That's what science does. You know, here we are up to this point. Well, how do we know Einstein's right? Guess what? People are still testing Einstein's theory to decide whether or not he was right. We may find that there's things we need to correct about what he said, right? Science doesn't stop. Science is like a giant circle. We keep testing it over and over and over and over again. Okay? So kind of go through these, maybe make a game out of it. Maybe cut these out and do like a matching game. See how many you can get. Okay? All right, so if you haven't done so already, read Module 1. Our first live class, we're going to jump right into the on your own questions, okay? So at least have read through those, or if you have your answers ready, that would be best, okay? Try some of the experiments. Try the one with Kepler, the one with the ellipse. See if you can actually see what we mean by an ellipse. Now, another way that we can kind of learn more about these scientists, because there are quite a few of them, is if you want to pick a one or two and write just a really short, very, very short report on them. Maybe just talk about, just a little bit about their life maybe and what they discovered. Upload it to the class page, and we can look at some of them in class. We may not be able to see all of them because I don't know how many we're going to get. But I will take any ones that are turned in, and I will put them in another section where you can actually look at them on your own, okay? So we'll try to look at them in class, but if not, we can kind of read each other's, okay? So if you want to do just a little quick report, maybe even put a picture of him or a picture of something that he did, like Leeuwenhoek, you could put what would the first microscope look like, that kind of thing. Okay, all of this is just to help you and help the other students remember these scientists. This is not graded. This is optional. Okay, don't think you have to do this, but sometimes, you know, maybe studying one or two scientists more in depth might help you remember them better. Okay, all right, and we'll look at as many of them as we can, but study that timeline. Okay, and just look at the important thing that each one of them did. I try to minimize what it said. Just think of the things that they did, because what the test is going to look like, it's going to be matching. It's going to be a matching. It's going to say Sir Isaac Newton, and you're going to have to go down the list and figure out what he did, right? Not all of these scientists will be on the test, and you'll see that's true with all of these modules. Not everything we talk about in class is going to be on the test. We need to look to the study guide. So we'll pay attention to what the study guide tells us, okay? The other thing to keep in mind with this chapter is the things that we learned about. Remember, culture and government are important for science to continue. And that it was the switch between the Roman thinking and the Christian thinking that got us out of the Dark Ages, right? All right, so those are two concepts that we learned. Oh, and the third one, of course, is we don't trust the scientist, right? We look to the evidence, okay? So there's some questions on there about those kind of things too, all right? So I'll see you in class, on the live class, and we'll go over the on your own questions, okay? All right, and if you have any questions, you can post any kind of questions you want on the class page under any assignment, or you can go to the very top, see what it says on the far right-hand side, and you click on that button, and you can see my name in there, and you can just click on that, and it will send me an email. Okay, so you have a question before class starts, or during class. Okay? All right, I'll see you in class.